A revision video for students studying for GCSE. It can be any board, so I'm just using this PowerPoint as a general reminder of the things that you've studied in different topics. So forces and motion for GCSE normally covers equations such as these. This is the AQA physics equations sheet. Now there's rumor that they're going to give more equations again, as they did during COVID years. So you'll notice all the equations. You need to know Newton's second law, forces mass times acceleration, and you need to know the acceleration is change in velocity, which is final velocity v minus initial velocity u divided by time taken. So these tend to be the GCSE and above symbols used for the different terms. So you need to know that these different terms, you need to know, for example, initial means starting velocity and v means final velocity. W equals mg, m is mass, g is the gravitational field strength. For Edexcel they use 10. I can't remember what they use for AQA. So it's the conversion of mass on Earth to weight in newtons. So weight is in newtons, mass is in kilograms. You need to know the units for each of these terms that are used. So for example, up here, newtons is capital N, acceleration is meters per second squared. So G, gravity, as it's often symbolized, is gravitational field strength, which is the acceleration caused inside the field, and it can be measured in meters per second squared. Okay, that's how much it accelerates. And if you think about it, meters per second squared comes from this equation, A equals V minus U over T, where V minus U will be in meters per second and T will be in seconds. So you're dividing meters per second by another seconds. So acceleration will be meters per second, but we don't write meters per second. Usually the shorthand form is meters per second squared. Okay, that's why it's this unit, and that confuses some students. So acceleration due to gravity is really more of a acceleration than a force. And if you write the force is gravity, you will lose a mark in many exams, because the force is actually the weight, yeah, and the force depends on the size of the mass and the gravitational field strength. The other unit you could use for gravitational field strength is newtons per kilogram, because it basically converts kilograms into newtons. Yeah, so if this side is newtons, this mass is kilograms, then this must also be newtons per kilograms. So units are a really useful way of analyzing if the equation, what the equation is telling you, and what each quantity in the equation actually means. Here you got Hooke's law, F equals KE. Sometimes E extension is also used in other exams as X. I think Edexcel use X, and it looks like over here the AQA exam sheet uses E. So you just got to be familiar with what the equations are for your exam, okay? And then work done is force times distance. So if you've got a force and you're applying it, for example, you're lifting something against gravity, you've got to apply a force equal to the weight, otherwise you won't be able to lift it. And then you can lift it, and the distance that you move it, like the height, say you're lifting a box from the floor onto a cupboard, the distance moved will be the height of the shelf or the top of the cupboard, and must be in a direction of force. So that's what I'm saying. If you're lifting something, you're working against gravity, you're doing the work, the physical work, and then you're transferring the energy higher in the gravitational field, so you're increasing its potential energy. Okay, so there are other equations that they haven't put on here, and it's really a good idea for you to learn your equations, because, for example, they haven't put kinetic energy on here. Yeah, you need to know your equations. But if you don't know your equations by the end of your GCSE, it means you really haven't studied hard enough. Okay, so that's the equation sheet, some of the equations for forces and motion. And over here is a year 9 equation which says speed is distance over time. They won't give you some easy equations like that. And then right now you'll see that distance, we don't really use distance as d most of the time in GCSE. The distance becomes s, and the speed we use as velocity, so it will become a v usually. Okay, so I'll show you on the next sheet where I've changed it. So distance over time is more of a year 7, 8, 9 equation, okay? But you do need to obviously use it in GCSE. For example, the average speed travel will be the total distance traveled divided by the total time taken, but it may not be that you're going at constant speed all the time, okay? So for example, here's a distance time graph. So as your distance is increasing, that means you have a certain amount of speed, otherwise your distance wouldn't increase. So the gradient of the distance time graph gives you the speed, yeah? So you could work it out if you had numbers on the distance axis and you had numbers on the time axis. You would divide this distance over here by the time over here, and you'd be able to work out the speed. So this is a medium speed. The green arrow is a faster speed, so you'd write here fast speed, medium speed, and the blue arrow is less steep to start with, yeah? But you can see it's not a constant gradient. That means the speed is changing. Whereas over here, if it's a straight line, it's a constant speed, yeah? But the green speed is bigger than the red speed. If it's a horizontal line on the distance time graph, you should notice that the distance doesn't change. That means you've stopped, yeah? For example, a pedestrian may be walking down the street, wants to cross the road, but cars are passing, so it waits until the cars stop at the red light, and then it can cross the road at the end, yeah? And this is a negative speed because the gradient is downwards. So the gradient or the steepness of the slope tells you about the speed or the velocity. Okay, so fast, steady speed is the green one, steady speed is the red one, stationary is horizontal line, and getting faster is a increasing gradient. Okay, if the gradient was decreasing, it would be getting slower. Okay, and finally, returning to the starting point means goes back to distance equals 0. Okay, so this is basically the first motion graph you have to do. The second one is they will expect to know the difference between speed and velocity. So what you know, speed is simply how fast you're traveling, usually in meters per second, but it could give you kilometers per hour. They could even give you miles per hour. Sorry, but there's a vacuum cleaner going on in the background, but I'm going to continue. Okay, so this is a old French car, a 2CV. The car is traveling at 20 meters per second. Yeah, we don't care which direction it's traveling. We just simply want to know how fast it's traveling. But if we say the speed with a given direction, it's then defined as a velocity quantity, and that this means the direction must be given as well, and that it's more than just the speed. Okay, and this car is traveling with a velocity of 20 meters per second, the same car, and it's telling us that it's traveling eastwards. So that would be a velocity, whereas the first one above, just the 20 meters per second, is just the speed. Okay? The second type of graphs they want you to know about a velocity time graph. Yeah, so remember I told you in the equation sheet, if you're dividing meters per second by seconds, yeah, this time they're giving you the numbers on the axis, you can actually work out the steepness, and the steepness would be velocity divided by time, or the change in velocity divided by time, and that means the gradient is the acceleration. So that means that yellow line is accelerating, and then it's going constantly at 40 meters per second, so it's a constant velocity or a constant speed. Because it has no direction, it's true in both senses. Then it's accelerating. You'll notice this line, the next line here where we haven't written in the box, is not as steep as the first one. That means the acceleration is not as fast as the first line. And you could work it out. This 40 divided by 10 means it's accelerating 4 meters per second every second, or 4 meters per second squared, whereas over here it's gone from 40 to 60, so it's 20 meters per second in 10 seconds, same time duration between here and here, and the initial acceleration phase. So that would be 2 meters per second, or 2 meters per second squared. And then downwards velocity time graphs, negative gradient is a deceleration or a negative acceleration, because v is 0, u is 60, V minus U is minus 60 divided by 20 seconds. So it's minus 60 divided by 20 will give you a deceleration of 3 meters per second squared, or an acceleration of minus 3 meters per second squared. Okay, so deceleration is a negative acceleration. So these are the equations I told you about before, and these are the GCSE equations, and the only one they've missed out on here, because you don't need it for the acceleration equation that they've given you, is S, and S for these what are called SUVAT equations. SUVAT spells SUVAT, and they also use these in A-level. So S would be the displacement, or the distance with the specific direction in mind. Okay, so that's the end of the motion graphs, and then the forces and energy are combined really for the next few slides, so we'll have a look at it. I explained this in a previous video. So that Newton said an object will continue to move in a state of constant velocity unless acted upon by an external resultant force. They call it a net force. That's Newton's first law. So every object, like this ball, will, once it's moving, will keep on moving at that velocity. And in space, if it's far away from a gravitational field, it will just keep on moving without changing its velocity. If it approaches another planet, or it goes close to a planet or another gravitational attraction force, it will then change its velocity, accelerate in the direction of the unbalanced force, also called the resultant force. So that's Newton's first law. Okay, acceleration is 0 in Newton's first law. Yeah, and of course, if someone comes and pushes the astronaut, same thing will happen to him. So be warned, if you go into space, make sure you're tethered to whatever you came from, like in the space station. If you go and do a spacewalk, be careful. If you haven't got a cable attaching yourself to the space station, you won't be able to get back. Okay, unless you've got a rocket on your back. Okay, so Newton also said every action has an equal and opposite reaction. So when the astronaut throws the red ball, he will actually go backwards, because the action on the red ball creates a reaction on the astronaut himself. The ball went faster because it had less mass, and the astronaut goes slower because he has more mass. But if you actually multiply the mass by the velocity of each of the objects, one in the positive direction to the right and the other in a negative direction, if you actually multiply their mass times their velocities, the quantity of mass times velocity, also known as, for those of you who studied it, is momentum, will be equal in opposite directions. That's why guns recoil. So, and also how rocket engines work. So if you fire a gun, the bullet goes with high velocity forwards, and the gun will push you back because it gets the recoil momentum. Okay, and the actual momentum in both directions, as I said before, are equal. So that's how a rocket engine works. Rocket expels a mass of gas from the back, and that pushes the rocket forwards. Okay. That's all Newton's third law. Okay, so you could actually use Newton's third law to slow yourself down by ejecting the gas thing. So that was actually it didn't show you that he's releasing the ball there. I think there must be a slide missing in this sequence. But I've got a video just on these slides where it's explaining how the astronaut does it. So go and have a look for that video as well. Okay. So resultant force means simply the difference between two forces, because forces, like velocities, are vector quantities, and you need to take into consideration the direction of the force. So an engine that is firing its rocket engines, and the exhaust gases come out the back, if you just look at the forces on the orange rocket, once that produces a thrust forwards, or upwards in this case, and there will be some drag, but the difference between the resultant force on the rocket upwards will be greater than the drag force initially, and that's why it will accelerate upwards. Okay, so when we're looking at resultant forces, we're actually looking at Newton's second law, yeah, and we're looking at cases where one object, we're analyzing one object, in this case the orange colored rocket, it will be propelled forwards because the forward force on the rocket is greater than the forces acting against its motion. In this case, it will be weight, and it will be a little bit of drag, and the drag will increase as it increases speed. So resultant force means the difference between the forces in a straight line, and most of the questions you'll get in GCSE will be in a straight line. Once you get to A level, they'll give you forces at different angles, and you have to do more mathematics on it to be able to analyze it. Okay, so resultant force means the net force or the unbalanced amount of force. Okay, so balanced force is Newton's first law, and unbalanced forces is Newton's second law. So you see the red arrow is bigger than the blue arrow, so the upward forces are greater than the downward forces, and that difference between them, if it was 60 and 20, would result, yeah, hence the word resultant. The result would be 40 newtons upwards, okay? And 40 newtons upwards shows the length of the arrow is the size of the force, and the direction of the arrow is the direction of the force, or the unbalanced force. And that's why force also, like velocity, is a vector quantity. It has size or magnitude and direction. So acceleration is the consequence of a resultant force, and that's where Newton comes in. So here you see the orange bus, you got the engine and wind, it says, pushing it 6 newtons to the right, and air resistance slowing it down with a force of 3 newtons. The arrows have not been drawn to scale here, so the resultant force, if the resultant force is 0, the object will remain motionless or continue at constant speed, like we showed you in the space example. So resultant force, when the resultant force is 0, the acceleration is 0. When the resultant force is not 0, there is a non-zero acceleration. And so 0 means Newton's first law. Acceleration of 0, or resultant force 0, is Newton's first law. Yeah, the object will continue at its state of motion. So whether it's stationary or moving at constant speed, it won't change. It won't have an acceleration. But when there is an unbalanced force or a resultant force, it will accelerate. Okay? All right, so the resultant force, as you see, is 6 newtons in the blue arrows, 3 newtons in the right, in the arrows going to the left. The difference is a resultant force of 3 newtons. Once we know the resultant force, and if we know the mass, you will be able to work out the acceleration. Now, braking is exactly the same as the resultant force, this time against the motion. When you need to stop a vehicle, so for example, the red light ahead, the velocity of the vehicle will decrease when the brakes are first applied, and obviously 2 things will affect how quickly you can stop it in terms of once you put the brakes on, is the velocity of the vehicle will make it more difficult if you have a high velocity to slow down the car, and the mass of the vehicle, if you have a more massive car, it takes more energy, therefore it will take longer for the forces to be able to do what they need to. There's also a reaction time involved when you're trying to react to, say, the red light suddenly coming on. Your foot has to move from the accelerator pedal to the brake pedal, and that distance you travel while you're reacting to the need to brake, for example, is called the distance you travel while you're thinking. It's called the thinking distance. So once you've got the thinking distance, that will be at constant speed while you're changing your foot from the accelerator pedal to the braking pedal, and then the brakes will apply and the speed will go down. So actually, during the thinking phase, your speed more or less stays constant. Okay. And unless you're just cruising and you don't have your foot on the accelerator at all, it will slow down due to air resistance. But the brakes only come on once you move your foot across, and that takes a bit of time. And because you have speed, you're actually traveling a certain distance while you are reacting to the need to stop. Okay, so this is the stopping distance equation, which I taught my students in year 10 this term. Okay. Now you'll see that as you go faster, these look like they're in miles per hour or kilometers per hour. As you double your speed, yeah, the thinking distance is the yellow bit, is increasing in a linear fashion. yeah, more or less. They've done it in terms of car lengths rather than exact meters. But you'll see that the braking distance gets much higher for double speed. So you go from 30 to 60, 4 car lengths for 30 for braking, how many for 60? Yeah, so you count how many car lengths: 2, 4, 6, 8, 9. Yeah, so um, actually, what happens with the braking distance is that every time you double your speed, you should quadruple the braking distance. Okay, and there's a mathematical equation linked to kinetic energy, which has a speed squared function in it. Okay, so the thinking time increases more as a straight line, but the braking distance is much more difficult and it's more of a curved change. Okay, it's not directly proportional to the speed. It's the speed is really important. So obviously, the faster you travel, the more braking distance you need to leave in front of you so you can stop the car safely. So factors that affect stopping distance also, they ask you in GCSE, very common. Over there, the sign says tiredness can kill. Take a break. So when you're driving, if you're tired, your reaction time is slower. So the time you take to react to an emergency, for example, will be higher. The weather also, if you've got wet roads, the friction is less. So your tires will not be able to have such a good grip, and you won't be able to stop as fast. Other things, so things that slow you down in terms of being able to react, are tiredness, some alcohol, and some drugs. It could be medication, for example. Okay, the speed that the vehicle is traveling at, obviously, we explained that on the graph before. The speed affects both your stopping distance, your thinking distance, and your braking distance. Poor road conditions, adverse road conditions. It's better to write like wet or icy roads in the exam so they know exactly what you mean. And you say wet and icy roads increases your stopping distance rather than just say affects your stopping distance. Make sure they know that you understand which way it will do. Poorly maintained vehicle is a general term. You could say condition of the brakes. If the brakes are old, they may not be able to stop the car as efficiently or as quickly. Okay, so make sure you explain it really in a crystal clear fashion. Okay, don't just put the words down. Explain, describe why it happens that way. All right, mass and weight we talked about already. Mass is in kilograms in SI units, weight is in newtons, and the conversion between them is called, for Earth is 10 newtons per kilogram, and so W on the equation sheet you saw is equal to mass times G, the gravitational field strength. Okay, on the moon it's about 1.6, and if they give you other planets, they will give you what the gravitational constant for the planet in question would be, and they will ask you questions to do with forces. So, for example, the man has a mass of 120 kilograms, presumably with his spacesuit on, and his weight at the surface of the Earth will be 1,200 newtons because you just multiply the mass by 10, and on the moon you can see that it's the same man has the same mass but a lower weight because the moon is much smaller, so its gravitational field strength is lower, and as I said, it's 1.6, so hopefully 120 times 1.6 will approximately be equal to 200 newtons. Okay, so I hope that makes sense. And then when we did forces of motion, we had velocity time graphs. In this case, it's a speed time graph, and they love this question, so they need you to explain why does a skydiver, when he jumps out of the plane, initially accelerate at the G, the full value of gravitational field strength, and then the rate of acceleration decreases until he can't go any faster. That's called the terminal speed, and the reason is, at first, he has very little air resistance. The weight is greater than the air resistance, so you can accelerate maximally or at a maximum rate. Once the air resistance builds up, it will at one stage equal the weight, and that means you can't speed up anymore. You're still moving downwards at a rate here of about 50 meters per second, but you can't accelerate anymore, and then you want to hit the ground. You don't want to hit the ground at 50 meters per second, so you open your parachute. The parachute has a much bigger amount of air resistance at that speed. So suddenly the air resistance is greater than the weight of the skydiver. Over here is a 70-kilogram man. Looks like a man. So 700 newtons. Okay. So the weight doesn't change in all three pictures. Yeah. The weight is constant. Air resistance starts at 0, increases gradually 700 as the speed increases, and then when you open the parachute, because it has a much larger surface area, the air resistance will suddenly become larger than the weight, so that will decelerate you, and then eventually the man will slow down as he falls, and the air resistance will decrease because air resistance is basically proportional to speed. So over here, he'll then reach a second terminal velocity, or terminal speed as they called it here. And this terminal speed, where the weight will equal the air resistance again back to 700 and 700, but it happens at a much lower velocity, less than 10 meters per second according to the graph they've given us. And that's a safe speed to land at, and this is where his feet touch the ground, and his legs will be able to handle that deceleration in the landing. Okay, so this is a very common equation, and you should be able to show which part of the graph is represented by what kind of force diagram. Okay, so here you got unbalanced forces, therefore acceleration, Newton's first law. Here you got balanced forces, therefore Newton's first law. The object will continue to move at its constant rate of speed until another force acts on it. Here you then got another force acting due to the parachute, and therefore the forces become unbalanced again. So it's again Newton's second law, and this time it's acting against the motion, so it's a deceleration, sudden deceleration, quite a steep line. Yeah, and here you got balanced forces again, and that's the end of the analysis of force diagrams. Velocity time graphs is a perfect thing to give you, and in a question I gave my students in year 10, instead of having this happen to a skydiver, they had a hailstone falling from a cloud, and of course a hailstone does not need a parachute because it doesn't care about slamming on the ground. So they were asking, why does the hailstone accelerate at first, and then why does it reach terminal velocity? So it's the same kind of analysis in terms of balanced forces and unbalanced forces. So I hope you found this useful. I'm not going to go into the elastic potential energy yet because we'll do some more on this section. The main section I wanted to cover was forces, motion, and we'll come back to do how energy is involved, because obviously as the skydiver is falling, he's converting his potential energy, yeah, although it's not elastic, he's converting his gravitational potential energy into kinetic energy, and we'll have another look at it in a second video because I don't like the videos becoming too long. I hope you found it useful. So when you're revising, make sure you're making notes, and you should make your own notes. For example, this graph will be a perfect set of notes, and it all fits on one piece of paper. Okay, so show what you can do in time for your mock, which in our school will be in January. Okay, well, if you found it useful, please support my video channel, my YouTube channel, by liking and sharing it with your friends so we get more subscribers. And please do subscribe, because we need 1,000 subscribers to make the channel viable and keeping it going for the future. This is the first year of this channel. It mainly focuses on A level, but it's now also having a big GCSE section added to it. Okay, so please subscribe if you haven't done so yet. Thanks for watching, and see you in the next video. Bye for now.